Okay, our next speaker is Asheesh Lanba. He's a mechanical engineer with 15 plus years in research, teaching, and entrepreneurship. And he's an assistant professor of mechanical engineering and the director of research at the Composites Engineering Research Laboratory at USM. I hope I still have that right. He teaches material science and math-based courses where he also gets to shoot stuff with lasers, break stuff apart, and put things together. He's lived in Maine since 2019. Outside of work, he's an avid hiker, mountain biker, cinephile, and sinophile. Every year when I ask people their favorite kind of pop coaster, there's always at least one person who's like, "Oh, I can't believe you make me pick. There's so many." That honor goes to you this time.
Thanks.
And you settled on Rick and Morty, which is excellent.
All right, thanks, Kate. Yeah, so Kate reached out to me and she wanted me to talk about one of my projects, and I was like, why don't I talk about all of my projects? So I'm going to talk about the group that I started at the University of Southern Maine, the Lasers and Materials Engineering Group, which the acronym for that is LAME. That's what you get when you have engineering students decide what your group name is going to be. They thought I wasn't going to pick it, but I was like, as an engineer and our obsession with acronyms, I think this is amazing. So we did that. Our group's focus is on three areas. We develop and test new materials, we shoot stuff with lasers and do imaging, and we also develop engineering applications like medical devices. And today I'm going to talk about one example of all of these three things. So on the materials side of things, this is what Kate reached out to me to talk about. We've started a company based off of work that was done at USM called Stoke Plastics. Now, we know plastic pollution is a big problem facing humanity right now. In particular, we produce approximately 12 million metric tons of ocean plastic waste every year. And, we really need to do something to turn off the fossil fuel tap and reuse and recycle these plastics. So what we've done is we've developed Stoke plastic pellets, which have more than 25% by weight of recycled plastic bottles that are ocean bound and ocean found to make injection mold dense hard goods. So recycled plastic bottles are great, and they're used to make textiles and thin wall cylinders like bottles and stuff like that. But what we're doing is we're making dense hard goods. And we actually have a minimum viable products of sunglasses and skiing goggles that we actually sell as well. So we are a small company looking for funding. So if any of you are rich and want to give us money, we'll take it. Next, with the laser side of things, for the better part of a decade, I've been working with this technology called laser ablation tomography, whereby we use a high-powered laser to basically cut stuff up and image it. And the cool thing is that after you cut something with this laser, you are left with an illuminated surface with the laser, and we see fluorescence due to the laser interacting with the material. So we get lots of color data, which is not available via other technologies, right? So we can then stack these images up and make 3D models, but comparing with X-rays and MRIs, you only get what's black and white grayscale data, but whereas we get full color data. So this is an example of one of the models, and it's not going to work. So this is a stink bug. How we used to get samples in our lab was they used to fly into our window. So these are the images that we get, and they get stacked up, and we just remove the black color. So you're left with all of this color from the laser-induced fluorescence, and then you can look at the anatomy and structure, which this is like a 2D and 3D microscopy tool for researchers that wasn't available to them before. Right now we have ongoing collaborations throughout the country, but particularly we started a collab with University of Maine, where they make a lot of wood-based products and paper and stuff like that, and they make things and use them, but they still don't know what they look on the inside, so they can't do any processing tuning and stuff like that. So that's what we're going to be helping them with. So really excited to be working with that. And then finally, on the medical devices side of things, since I've come to USM, it's going to be 6 years now. We've been working to develop cheap prosthetic arms. This is like really good for engineering students to work on. It's a good motivating project for them. So the goal to make cheap prosthetics that can be given to people who don't traditionally have access to them. This is like one of the fancier ones where he was able to use his muscle twitching to get the arm to start moving. We also make these arms and then go out to the Dominican Republic and give these prototypes out to testing to people who don't traditionally have access to them. It's always amazing seeing, a smile on their faces after they're done with that. And then, yeah, we have a program where we do and give out arms. We're moving to a program where we are starting to do leg stuff as well. Unfortunately, leg stuff needs a lot more testing because it's worse for you if you fall down, whereas if you drop something, right? So, yeah, that's a snapshot of all that we have going on at USM. That's my email if anyone wants to get in touch with me, LinkedIn as well. And yeah, just wanted to give a shout out to what's really important, right? We're doing this for the future and all the good work. And a lot of acknowledgements for everyone that's made this possible. We are funded by the Maine Technology Institute, the Maine Economic Improvement Fund, the Maine Space Grant Consortium, NASA, NSF. So it's really important to, I'm very privileged to have come to the US and just been able to play around with things. So yeah, thanks.
Any questions? Come on down.
I'd like to know, for your imaging, how long does it take to do that? And are you just doing the surface, or can you penetrate into depth?
So it is literally, so that's a great question. So typically what we do is, so for example here, this was a root that we had imaged, right? So it needs to be hanging off like a cantilever beam for it to be cut. And we are penetrating it. So we're physically cutting it and then taking an image of the flat surface that's there. And then we push it in again, we cut it, take an image. Due to all of the automation that's possible, and how quickly and powerful the laser is and how quickly it can burn stuff away, it's pretty quick. So this root over here, which is roughly like, let's say, 10 millimeters wide and 3 millimeters across, took like less than 2 minutes for the imaging to get done. That's not what takes time. What takes time is the reconstruction, because a lot of computer processing is involved with that. And that's a big challenge we face, is that right now, in order to do stuff in a timely manner, we have to like downsize all our images so that we can do it efficiently. So yeah.
The prosthetic arms and legs, how much are you able to produce? Is that 3D printed? And then the one before that, the movement, are those like off the shelf kind of things that you guys design and put in there?
Correct. So it's sort of, all of this is cobbled together. So a lot of the models that we use for the fingers and the palms and stuff are open source and available online. The putting it together and attaching it all to the motors and stuff with the computer and everything, that's what the students came up with, and that's what they did. And yeah, all of these parts are available online, and you can buy them, and you can do this yourself. It's great. I mean, the internet is, a lot of bad things happen on the internet, but a lot of good things happen on the internet as well. You guys can access all of this information and build these things. YouTube is insane. It's amazing. And that's how these students really do it. Engineers don't know how to do things. They just know where to look and figure out how to do things. So, yeah. And then...
Is that an Arduino or a microbit? Oh.
Yeah, so Arduino right over there. That's what's called a MyoWare thing. And this was awesome. The student got it working, but an issue we found was that this twitching was different for different people. So it wasn't a consistent solution that we could apply throughout. So, yeah.
So what happened when other people did it?
I couldn't get it to work, whereas there were a couple of other students who were able to get it to work and things like that. And it was also a little too heavy. This ended up weighing too much. So we have a much simpler solution right now with just one motor going on, and with like a garage door opener that we use right now. So, yeah.
Is AI advanced enough to be able to be of use to you, and are there significant ethical concerns about it?
That's amazing question. So I was first exposed to AI in 2016 when I first started working with the imaging technology, because the researchers are not just interested in looking at things, but they are interested in how many cells are in there, how many different kinds of cells are in there, right? And one way to do it is you physically go in and you label it on like your computer, and then you count the pixels and things like that. Very laborious process. What we can do is we do that labeling for like 20 images and then give it to an algorithm which will then do it for the remaining 1,000 images and give us those predictions. And then we can actually start looking at trends and science and things like that. So yeah, I've been using AI for the longest time. It does need regulation 100%, but for me, I have no fear of AI. I think it's just a tool that we're all going to use to be more productive at what we do. I use ChatGPT all the time for my writing now, so it's awesome. So yeah.
What are some potential real-world applications, like in medicine or in any field, of the laser technology?
Yeah, that's a great question. So the biggest project that a collaboration that we have going on right now is with the University of Missouri. And they are basically trying to understand how across the decades, as soybean plants started producing, becoming more crop efficient, what was the underlying cause for that? So one of the causes that they want to study is the amount of water intake that they had over the decades. So they have these cultivars of these plants from across the decades that they've grown in their lab, and now we image for them and we quantify what's called the vascular bundle, which is basically the blood vessels of the plant, and that's information that they use. So we help them provide them with like parts of the puzzle, so to speak, with this tool. So yeah.